Okay, so thank you to the organizers. It's a pleasure to be here and to see the new people here that weren't here last week at the workshop. So what I'd like to talk about, everything is joint work with Saima Samchuck-Schnarch, who is my PhD student in Ottawa. And these slides are on my webpage if anyone is interested. So what I want to talk about is developing a graphical calculus and try and make it as simple and intuitive as possible so we can use it as a tool for studying the real representations of real supergroups or real Lie superalgebras. So I'll start off with some background that'll be very lightning review of the things we saw in the workshop last week for those of you who weren't here. So I'll mention the oriented and unoriented Brouwer categories and how they're related to representation theory. And then to motivate the generalization that we'll see that will be related to real supergroups, I'll state Schur's lemma, which we all know, and discuss the relation to division superalgebras and maybe tell you some facts about division superalgebras that you might not have known. And then one other ingredient we'll need are super Hermitian forms over division superalgebras. So we'll recap those a little bit. And then we'll see the real Lie superalgebras that you get out of this data. Real division superalgebras and super Hermitian forms. And then that will allow us to develop this graphical calculus that will be basically a generalization of these Brouwer categories to the real world. Okay, so here's the background. So let's start off with the category that controls the representation theory of the general linear group. So this is the oriented Brouwer category. So it depends on some parameter D over our base field, which will be C. And so we have a category for each choice of this parameter. And the simplest way to say what this category is that it's the free, rigid, symmetric, C-linear monoidal category on one generating object, which we denote by an up arrow, of dimension D. So we learned all about what this was last week, but for those who weren't here, so rigid means you have duals. So we actually have a dual to this generating object. Symmetric means it's a symmetric monoidal category, so we should have things like crossings. You should think of that as being the flip of representations. And dimension D is that this object should have dimension D. There's a categorical definition of dimension, but you can think about representation of dimension D. So morphisms are pictures like this. I'm not going to get the precise definition of this category outside of this universal property because it'll be a special case of a category we'll see later. But they're diagrams like this. So you've got strands that are oriented, they can cross, you've got cuts and caps. And you can read the domain and the codomain of a morphism off the top by looking at the orientations of these strands. So you've got this up arrow and then it's dual, which is a down arrow. And the whole reason this category is important is because there's a full monoidal functor that goes from this category to the category of modules over the general linear group. Okay, so the fact that this is full means you're capturing all the morphisms between tensor powers of this natural module and its dual in the image of this functor. In particular, if you look at just the R-fold tensor power of this generating object, so on the GL M mod side, that's the R-fold tensor power of this natural module. Then if you think about strands where all the strands are oriented up, you can't have any cuts and caps, you've just got crossings, and this endomorphism is the group algebra of the symmetric group. This surjects onto this endomorphism space, and that's half of Schur-Bell duality. Okay, so you see that sitting inside this bigger picture. Instead of the general linear group, we want to consider the orthogonal group or the symplectic group. Then we lose the orientation. So we have an unoriented Brouwer category, which again depends on this choice of complex number. So now it's the free, rigid, symmetric, C-linear monoidal category on a symmetrically self-dual object. So now this object is dual to itself. And that means that our pictures look something like this. We lose the orientation because instead of having one object in its dual, we just have an object that's dual to itself. Okay, but Brouwer diagrams are probably even more well-known than the oriented Brouwer diagrams. And so our monoidal category, its morphisms are linear combinations of these types of diagrams. Composition is stacking vertically, and tensor product is horizontal juxtaposition. And the reason these are important is that there are full monoidal functors from this category to modules over the orthogonal group or the symplectic group. And you see for the symplectic group, this parameter is actually negative. So there's a slight difference between categorical dimension and real dimension, in the usual sense. And then the endomorphisms are Brouwer algebras. So if you look at just endomorphism algebras, you get the analog of Scherval duality in the orthogonal and symplectic world, where you have Brouwer algebras. That actually came before the definition of this category. Okay, so a few remarks. The first remark that'll be important for us is that if you move to the super world, actually things get a bit simpler, things get unified. In the oriented case, you can actually replace the general linear group by the general linear supergroup. So it's the exact same category, and you have a full functor to modules over GLMN. And now your categorical dimension is the super dimension, m minus n. And the orthogonal and symplectic cases get unified together, and you just have one full functor from the Brouwer category, again, where the parameter is the super dimension, two modules over the orthosymplectic supergroup. Okay. And then one observation that is quite trivial, but will be very important for us, is if you look at just the natural module, say, well, that's a simple module for GLMN. So its endomorphism algebra is just the ground field. It's just the complex numbers here. And the same thing is true for the diagrams. If you think of what kind of diagrams you can have on just one strand oriented up, it's just multiples of that single strand oriented up. You can't do anything else. So you have this isomorphism from just copies, linear, scalar multiples of this up arrow that corresponds to the fact that this simple module is endomorphism algebra C. And same thing in the unoriented case. So the only possible diagrams you can have are just a single strand up. You've got all multiples of that strand. That corresponds to the fact this is a simple module, and its endomorphism algebra is just complex numbers. Okay, so trivial observation, but it'll be important for us in a minute. Okay, so let's look at this in a slightly more general setup. If we fix some ground field K, so up till now it was just complex numbers, but now let's look more generally. And let's say all our supermodules will be finite dimensional through this whole talk. If we take some either associative superalgebra or Lie superalgebra over this field, well, Schur's lemma tells us that the endomorphism algebra is a finite dimensional division superalgebra over this field. Okay, so we saw that before over the complex numbers. There's only one complex division algebra. And if we're here, we're in the non-super case. So there's only complex numbers. That's the trivial observation, basically, that I made before. If we work over real numbers, I should not have the word super here yet. So we're still in the non-super world. So if we look over the real numbers, but non-super, then there are exactly three real division algebras. So those are the real numbers, the complex numbers, and the quaternions. So this trivial observation becomes a little bit more involved over real numbers, because those are the possibilities for endomorphism algebras of simple modules. And now let's go to the super world. So in the super world, let's start again with complex numbers. But now that we're in the super world, we have one additional possibility. So before we had complex numbers, but there is one other complex division superalgebra, which is the complex Clifford superalgebra. So its even part is just a copy of the complex numbers. Its odd part is generated by this one extra generator epsilon. So bar is my parity, so it has parity 1, it's an odd element. And it squares to either 1 or minus 1, depending on your conventions, and commutes with the even elements. So when you do Schur's lemma over the complex numbers in the super world, it tells you endomorphism algebras are one of these two things. Okay, so that means in the super world over complex numbers, there are two types of simple module. There's the one whose endomorphism algebra are the complex numbers, and there's the ones whose endomorphism algebras are this complex Clifford superalgebra. So those are called type M and type Q modules in the super language. Yeah, I think this comes from the fact that the endomorphism algebra here is matrices. It's a matrix superalgebra. And here's this type, it's usually denoted Q. This QM is the endomorphism algebra. I think that's where the notation comes from. Okay, so let's go to real numbers, super now. Okay, this is probably less well known than the other facts I've mentioned so far. Over the real numbers, there are exactly 10 division superalgebras. Okay, so it's not so hard to prove this once you think about this as a question you might want the answer to. Because if you have some real division superalgebra, the even part is just a usual division superalgebra, so it has to be RC or H. Any non-zero odd element is invertible, so it gives you an isomorphism between the even and the odd part, and then you work out a couple other possibilities and you see that you get these 10. So it's not so hard to prove this there. And if you look at it a little bit, so at the bottom we've got those complex division superalgebras, which are also real division superalgebras. You've got R and the quaternions, but then these new ones are again generated by a single odd element. And you see this is the one that's got two copies of R, an even and an odd. This one as well, the difference is the element squares to 1 or -1. Over the complex numbers, those are isomorphic because you can rescale epsilon by I. Over the real numbers, they're different. And then you've got the two ones where the even and odd part are a copy of C and then the copy of H. Okay, so you can prove these are all the real division superalgebras. So some remarks, these things that I denoted CL sub R are real Clifford superalgebras, and they're the only central real division superalgebras. So where the even part of the center is R. The other ones at the bottom, C and the complex Clifford superalgebra, the even part of the center is C. And the notation, the subscript has a meaning. If you tensor two of these, it's Morita equivalent to the one you get by adding the subscripts, where you take the subscripts mod 8. And another property that'll be important for us, if you take the opposite superalgebra of one of these, so the opposite superalgebra is just a copy of your algebra as a K module, and you reverse the multiplication up to the usual sign. So if you take the opposite of one of these Clifford superalgebras, you get the Clifford superalgebra for the negative of the subscript, mod 8 again. And then the two complex ones are isomorphic to their own opposite. For C, that's clear because it's commutative. And for the complex Clifford superalgebra, you just check that this math is an anti-involution that sends this algebra to its opposite. So what that means is if we work over the real numbers in the super world, that there are 10 types of simple module, because the endomorphism superalgebra can be one of these 10 division superalgebras. So the general philosophy now is that we want to take this oriented Brouwer category, and we want to enlarge it. So there was this trivial observation before that we could only have multiples of this upstrand. We want to enlarge it so that this endomorphism algebra is now a copy of this superalgebra. So we want to add into our diagrams the fact that these strands can carry some token labeled by an element in this superalgebra. In the unoriented case, we essentially want to do the same thing, but there's one other thing that happens. You can now take an unoriented strand with a token and you can twist it, and it gives you another endomorphism of that object. And this twist will correspond to the fact that we really want an anti-involution on this superalgebra as well. That corresponds to this map. Okay, so let's look to representation theory a bit. If we want to take the general linear Lie superalgebra, but with coefficients in a real division superalgebra, what do we get? So first of all, there's a simplification. You can check it if the odd part is non-zero, then in fact, there's no point in taking GLMN because this is isomorphic to GLM plus N. So you might as well assume that the N is 0. It's still not purely even because this D has odd part, but you might as well just consider those ones. Another fact is that replacing D by D op gives you an isomorphic Lie algebra, or Lie superalgebra. So if we want to enumerate all the Lie superalgebras we get in this way, well, this is what we get. So this op part cuts our choices for D in half, basically. So we could take our D to be this complex Clifford superalgebra of the real numbers, is CL1. This is called the split real isomeric Lie superalgebra, or sometimes the split real queer Lie superalgebra. If you take the complex Clifford algebra, you get the complex version of that, the type Q Lie superalgebra. And then there are these other ones you can take. Well, GLMNC, this is the standard general linear Lie algebra, superalgebra over C. The other ones don't really have names, but there they are. Those are real Lie superalgebras. Now, these are real forms of complex ones, because you can complexify. You can tensor over R with the complex numbers. And so what do you get? Well, it's enough to know what you get when you complexify these real division superalgebras. So obviously, if you complexify the real numbers, you get C. you complexify the quaternions, you get 2 by 2 matrices. And here's what you get when you complexify the other ones. Notice that the Clifford superalgebras that are opposites of each other are isomorphic after we complexify. So you get either this complex Clifford superalgebra or 1, 1 by 1, 1 matrix superalgebras, or a 2 by 2 matrix superalgebra with entries in this complex Clifford superalgebra. So you can just compute what they are. And so if you want to complexify the general linearly superalgebras, first of all, you notice it's just the same as complexifying this superalgebra where you take the coefficients. And then you use these facts to see what the complexifications of all these real general linearly superalgebras are. So for example, if you take this general linearly superalgebra whose coefficients are quaternions, you complexify, use the fact that the complexification of the quaternions are 2 by 2 matrices. So GLMN, whose entries are 2 by 2 matrices, is the same as GL2M2N. Similarly here, you take CL2R, you complexify, that gives you 1, 1 by 1, 1 matrices. Well, GLM, whose entries are 1, 1 by 1, 1 matrices, gives you GLMM. Right? So you can just see what all these complexifications are. So you see you get real forms of either the general linear or this isomeric new superalgebra, which are the only two possibilities of the complex numbers. Okay, so now let's turn to anti-involutions, because I said in this unoriented case, we're going to need an anti-involution. And let me motivate just why you want anti-involutions also just from the point of view of representation theory. So if we have some associative R superalgebra, A, and some right module over A, then of course the dual is naturally a left supermodule over A, right? We act on some function on the left by this, so it corresponds to acting on the right here by multiplication by A with the usual sign, because A has moved past a couple things here, but that becomes a left action. But in the unoriented case that we're going to look at, we're going to want to consider the fact where a module is dual to itself. In order to be dual to itself, it doesn't make sense for a right module to be isomorphic to a left module, right? So we need them both to be right modules in order for this statement to make sense. So we need to turn B dual into a right supermodule, and that's exactly what we can do with a superinvolution, right? So if we have a right A supermodule, that's the same as a left supermodule over the opposite superalgebra. So if you have an isomorphism between the opposite superalgebra and your original superalgebra, you can convert left modules into right modules, or supermodules into supermodules. So that's what we'll do. So for some of our definitions, we're going to want to fix an involutive superalgebra. So that's just a superalgebra together with an anti-involution. Okay, so it squares to the identity and it reverses the multiplication. Okay, so we're going to want to fix one of these for some of our definitions. And this anti-involution precisely gives you an isomorphism between the opposite superalgebra and the original superalgebra. Right? That's why we're interested in it. And so now, if we have a right supermodule over one of these involutive superalgebras, then the dual is again a right module. So it's just the action I mentioned before, but now we twist by this involution, and then that fixes the fact that it was naturally a left module. Now it's a right module. Okay, so that's the point of involutions for us. So now let's look at our list of real division superalgebras, and let's see which of them have an anti-involution. So this is why I took a moment to tell you what the opposite superalgebras were, right? So the complex numbers and the complex Clifford superalgebra are isomorphic to their own opposite. That means there is a superinvolution. But for these real Clifford superalgebras, remember, when you took the opposite, you negated the subscript. So that means actually that a lot of them don't have an anti-involution because they're just not isomorphic to their opposite. So you need R to be congruent to minus R mod 8, right? So that really cuts down the possibilities. So here are the only possibilities. The only real division superalgebras that admit an anti-involution are R, C, H, and the complex Clifford superalgebra. So when we do this generalization of the unoriented Brouwer category, we'll only be able to use those four. Okay, so here are the things you can have, right? So the real numbers, your only choice is the identity because your anti-involution has to be R-linear. Complex numbers, you've got two choices. Because it's commutative, you can take the identity, but you can also take complex conjugation. Quaternions, you can take quaternionic conjugation. You can't take the identity because it's not commutative. And for this complex Clifford superalgebra, you can check that this is an anti-involution. Okay, so explicitly there's the anti-involutions we're interested in. Okay, so other thing we can do when we have one of these anti-involutions is we can talk about super Hermitian forms. And this will be an important ingredient in how our generalization of the unoriented Brouwer category acts. So if we take some right supermodule over some involutive real division superalgebra. So we have one of these real division superalgebras together with an anti-involution of it. Here's a very general definition of the type of super Hermitian form you can have. Okay, so we'll pick an element nu that's plus or minus 1, which you should think of as corresponding to being supersymmetric or skew supersymmetric. And we put our involution into the notation. And so a nu star super Hermitian form, so it's an R bilinear map from V times V to our ground real division superalgebra. Homogeneous, so it doesn't necessarily have to be parity preserving, but it has to be at least homogeneous. So it's either even or odd. And such that, well, if you pull out scalars from the right, they just pull out for free. If you pull them out from the left, you apply this anti-involution up to the usual sign, because A is moved past the B and the phi, which could be odd, or bilinear form could be odd. And then the nu comes into the fact, as I said, when nu is 1, then we have the condition that this is supersymmetric. If nu is -1, it's anti-supersymmetric or skew supersymmetric. So a super Hermitian form, the reason they're important for us is that they give an isomorphism between V and V dual. And let me just reiterate that the super Hermitian form can be even or odd. In both cases will be important for us. So some examples, let's just take the examples where everything is even. So all the odd parts are 0. So if you take your real division superalgebra to be complex numbers with the identity, then a 1 identity super Hermitian form is just a usual symmetric form, and a -1 identity super Hermitian form is a skew symmetric form. On the other hand, if we take our involution to be complex conjugation, then we get a Hermitian form and a skew Hermitian form. Right? So this just gives us a way to consider all these types of forms at once in one notation. Okay, so what Lie superalgebras can we associate to a super Hermitian form? So we fix one of these real division superalgebras together with an anti-involution. We pick one of these super Hermitian forms. And then, of course, we can look at the Lie superalgebra that fixes this form. Okay, so it's a subalgebra of the general linear Lie superalgebra corresponding to V, and it's the ones that preserve the form. So by preserve, I mean precisely this. Or probably a more natural way to think about it is we precisely pick this Lie superalgebra so that the bilinear form is a homomorphism of modules and not just a bilinear map. And then we can also take the supergroup that preserves this form. Okay, so to every one of these forms, we have the corresponding Lie superalgebra and the supergroup. Okay, so let me just see or discuss what we get from these super Hermitian forms. What type of Lie superalgebras we get? Okay, we'll give an abstract definition, but this is what we get concretely. So remember, a real Lie algebra is a real form of its complexification, right? So if you have some complex Lie algebra or Lie superalgebra, a real form is some real Lie superalgebra, such that when you complexify it, you get back the complex one. So if you take the complex numbers, then the Lie superalgebras you get from these super Hermitian forms are precisely the orthosymplectic Lie superalgebras. That's the case when you pick an even form. And the periplectic Lie superalgebras. That's the case where you pick an odd form. Now, over the real numbers, you get a lot more, because there are a lot more choices for your real division superalgebra. So for the GLMND, we can pick any of the 10 real division superalgebras here. So we get all of these. I mentioned what they were before. And now with this super Hermitian form, now we need an involute of real division superalgebra. So now there are just those 4 choices, but we can still choose any of those 4. And then we get these least superalgebras that preserve that form. And in fact, you get all real forms of the general linear, the orthosymplectic, the periplectic, and the isomeric or queer from this construction. All real forms of these Lie algebras. And these are probably the most important least superalgebras. So you get all real forms of all of these in just one of these 2 ways. Okay, so now I want to develop this graphical calculus. Okay, so the concept of a monoidal supercategory is probably not so familiar to some people. So let me just briefly tell you what a monoidal supercategory is. We fix some ground field K. For us, that K will be real numbers or complex numbers. A strict monoidal supercategory, well, it's a category enriched in the category of vector superspaces. So what that means concretely is each morphism space is a K supermodule or a K superspace, vector superspace. And composition of morphisms is bilinear and parity preserving. So that's what it means just to be a supercategory. And the strict monoidal part means you've got a tensor product, which is a bifunctor. You've got a unit object. And that tensor product should be associative on objects. The unit object should act like a unit for this tensor product. It should be associative on morphisms. And the identity endomorphism of the unit object is a unit for tensoring morphisms. And the tensor product should be K bilinear and parity preserving as well. Okay, so that's a monoidal supercategory. It's just like a linear monoidal category, except for this, this fact that you're enriching category of superspaces instead of vector spaces. And so the string diagram formalism that we'll use is just like the string diagram formalism that we use for usual monoidal categories. So if we have a strict monoidal category C, a morphism from A to B will be a string going up the strand. So the domain is written at the bottom, the codomain is written at the top. The identity map is a string with no label. And often for us, the object will be clear from the context because, for instance, our strand will be oriented up, and then it's clear that the bottom and the top are an up arrow as the domain and codomain. So we usually won't draw those labels. Composition is vertical stacking of diagrams, and tensor product is horizontal juxtaposition. So far, this is exactly like the string diagram calculus for monoidal categories that we discussed last week in the workshop, and others may have seen in other places. The difference with the super world comes in this so-called interchange law, that when you're in a supercategory, a monoidal supercategory, whenever 2 morphisms change height, you pick up a sign. Right? So that's really the only difference when you deal with these in terms of diagrams, is you have to keep track of this sign that sometimes pops up when odd morphisms change height. The rest is all the same. And often we'll have a morphism whose domain and codomain are tensor products of objects. And that'll be some sort of picture where we have strands coming into and out of this picture, where the strands are labeled by the factors in the domain and the codomain. Okay. So now I can define these enlargements of the Brouwer and oriented Brouwer categories that we're interested in that are going to be related to the representation theory of real supergroups. So for our first one, this is the oriented version. We can pick any associative superalgebra we want. For our applications, this will be one of these division superalgebras. But for the definition, it can be any associative superalgebra you want. So we'll define an oriented Brouwer category associated to this associative superalgebra. So it's a strict monoidal category generated by 2 objects, up and down. In our applications, you should think of this as being the natural module and its dual. And here are our generating morphisms, things that we can use to build bigger pictures. We've got a crossing. We've got a token for every element of our associative superalgebra. And we've got all flavors of cups and caps. Okay, so if you haven't seen these diagrams before, let me just point out, if a diagram has nothing at the bottom, then the domain is the unit object. If it has nothing at the top, the codomain is the unit object. Otherwise, you can read off the domain and the codomain by the orientations of the arrows at the bottom and top. So what relations? So we can build pictures out of these by stacking them vertically and juxtaposing them horizontally. And then we impose some relations. Okay, so what are the relations? So this first row is just saying that the map from our superalgebra A to the endomorphism superalgebra of up arrow is an algebra homomorphism. Okay, so 1 gets sent to the identity, it's linear in the labels, and the multiplication is multiplication in the superalgebra. Okay, so this middle line, together with the first two relations on this line, are just relations that we impose so that this category is a symmetric monoidal supercategory. So the crossing should square to the identity, crossing should slide through strands, and these tokens should slide through strands. These ones are some compatibility between the symmetric monoidal structure and the duality structure, so the cups and caps and the crossings. And then these so-called zigzag relations correspond, as we saw last week, for those who were here, correspond to the fact that these objects are dual to each other. Okay? And if you'll notice, these relations here involve right and left crossings, which are in our generating morphisms. We define those from the up crossing by twisting them around with the cups and caps.
Alistair, none of your examples are going to have signs for the adjoint? For this?
That's right. It's because when you're in this oriented setup, you can always remove such signs because you can parity shift the down arrow, for instance. Where the signs come up is when we do the unoriented version, and it's the same object as dual to itself. You can't use this trick of parity shifting one of them. So in fact, you could define a category that's got some signs, but you can always just remove it. Now this is a supercategory, so I need to tell you the parity of all the morphisms. So a token labeled A is just the parity of A, and all the rest of the generating morphisms are even. So for an overall picture, you just are adding up the parities of all these tokens up here. So at the very beginning of my talk, I didn't give you the definition of the oriented Brouwer category. If you just take this A to be the ground field, then that's the oriented Brouwer category, or a presentation of it. So here's a picture of some morphisms in the oriented Brouwer category. They just look like oriented Brouwer diagrams. The only difference is our strands now can carry these tokens labeled by elements in this superalgebra, right? So it's not that big a change. And again, composition is vertical stacking, tensor product is horizontal juxtaposition. So as I mentioned, if you take this superalgebra to just be your ground field, that's the oriented Brouwer category over that field. If you take your division superalgebra to the complex Clifford superalgebra, you get the oriented Brouwer-Clifford supercategory, which has appeared before. So in particular, those are the two choices of division superalgebra when you work over the complex numbers. So we just recover things that people have seen before. The real new stuff is when you work over real numbers that we're interested in. Okay, so here's the connection to representation theory now. So we have a nice functor that sends this category to a category of modules. Okay, so let's fix some real division superalgebra. So there are 10 choices, remember. We don't need any involution, so we can pick any of the 10 on this list. And let's let V be the superspace over that division superalgebra of superdimension M, comma N, or even part M, odd part of dimension N. So here's the main theorem. There's a unique monoidal superfunctor from this modified oriented Brouwer category to the category of supermodules over the general linearly superalgebra with coefficients in that division superalgebra. You need to take actually the opposite here, and we'll see why in a second. So what does this functor do? It takes this generating object up arrow to the natural module, this natural module for the general linearly superalgebra. It takes down arrow to the dual. The crossing just gets sent to the usual tensor flip, right, in the super world. So we got this usual sign. It takes the left cap to just evaluation. And it takes this token labeled A op to right multiplication by A. This is why we need op, because our GLMN acts on the left. We want this A to act on the right. So because it's acting on the right, we need to take actually these labels to be in the opposite superalgebra. Okay. And so you should notice a few things. One is I haven't defined it on all the generating morphisms because I only defined it on the left cap. There was also a right cap and there were a cups, left and right cups. But it's uniquely determined by where it sends these three. So you don't need to specify where it sends the other cups and caps. And the main really important thing is that this functor is full. Okay, so actually this functor exists and you can define it, and it's not hard to show that you have this functor, and you don't need this D to be a real division superalgebra. It can actually be any associative superalgebra, right? And then that part's not hard. The hard part is showing it's full, and it's for fullness where we need this to really be a division superalgebra over the real numbers.
Is that when you prove that it's full, is the proof sort of uniform in all these examples, or do you have to look these like
It is not at all uniform. I'll mention the difficulty in a second.
Do you not need some M or N in the oriented parallel?
Yeah, so it's the bubble. So if you notice at the beginning when I defined the oriented Brauer category, I had just parameter D. I didn't give you the definition, but it's that a circle is equal to D.
But what is that?
So this factors through a quotient of this category I defined, where you have the bubble evaluates to something that involves the n and the n. It's not exactly Mn because you've got the superalgebra A. You have to take this sort of trace map of A and then multiply by m minus n. Okay, so when our ground field is the complex numbers, and there are two choices for this complex division superalgebra, remember complex numbers are the complex Clifford superalgebra, then those results were known, right? So the new thing is really the real numbers here. No, we just cite the existing literature. No, because our proof, as I'll mention, ends up using this complex case. Yeah.
Why is it right multiplication?
Well, because we want our naturally if you want to think of this as both, some module in this category, it's both a module over GLMNP and over D. You want the D to act on the right because the GLMN walks on the left. You can put everything on the left, but then it is just awkward. It's better to have it on the right. Okay, so that's the oriented picture. Now the unoriented picture, now, as I hopefully motivated, we need this division superalgebra to have an involution. So now there are just 4 choices because we need to admit an involution. And we need to pick some parity. You should think of this as being the parity of the bilinear form when we were discussing super-Hermitian forms. The parity of that form is the sigma. So now we have a whole family of modifications of the Brauer category. So they depend on this choice of sign, our ground field, and this involutive division superalgebra. So our morphisms are a crossing, a cup, and a cap, and these tokens for everything in our superalgebra. And what are the relations? Well, this first set of relations, same justification I gave before. It's because we want the map from A to endomorphism algebra of this generating object to be a algebra homomorphism. Then we have the relations that make it a symmetric monoidal category. That's these first 2 here. This fact that crossings slide over caps and tokens slide through crossings. So those 4 together, just we impose them because we want our category to be symmetric monoidal. This is a fact that this generating object is self-dual. And here we see the sign that Aaron mentioned. There are 2 possibilities. This object can be dual to itself or dual to the parity shift of itself. When it's dual to the parity shift of itself, we have to put in this sign. And we can't do this trick of parity shifting that away because we have to parity shift it twice. It just cancels. And then this relation is some compatibility between the symmetry and the form. It's that your form is skew Hermitian or super Hermitian. And then here, this is the only place you see this involution. It said these tokens, when they slide over a cap, pick up this involution and a sign. This corresponds to the motivation I mentioned way back at the beginning, that this involution comes from twisting this strand, right? This is where you see that here. And again, this is a super category, so I need to tell you the parities of all the morphisms. So again, these tokens, their parity is just the parity of the label. But now the cups and caps have parity the sigma we chose. So in the case where we have a minus sign, the cup and the cap are odd. Otherwise, they're even. And then the crossing is even. Okay, so morphisms in our category, I put oriented. This should not be oriented anymore. So, and I should have a sigma. Sorry, I just rewrote the other one. So morphisms in this category just look like morphisms in the Brouwer category, except again, we can carry, strands can carry tokens labeled by this division superalgebra. Composition is vertical stacking, tensor product is horizontal juxtaposition. So what are some examples that appeared before? If you just take your division superalgebra to be the ground field, then this is the Brouwer category. When you take sigma to be 0, when you take sigma to be 1, it's the periplectic Brouwer supercategory, or these authors called it the marked Brouwer supercategory. There was a special case of their marked Brouwer supercategory. And then we have the relation to representation theory, which is the whole motivation. So we fix one of these involutive real division superalgebras. We again pick our V to be dmn. And now we fix some non-degenerate new star super Hermitian form of parity sigma on this space. And we again have a functor now from this modification of the Brouwer category to modules over the supergroup that fix that form. Okay? So you should think of this as some generalization of OSP or periplectic, that flavor of supergroup. So it sends a generating object to this standard module. It sends the crossing to the tensor flip. It sends the cap to this form, and then you take the even part of the real part of that form, because it needs to land in real numbers. And this token, again, is right multiplication by A star. And this superfunctor is full. Again, that's the sort of the main part of the theorem. It's not hard to show that this is well defined. It's the fact that it's full that's the important part. So again, when we just look over complex numbers, these are results were previously known. So in the even case where your form is even, then you're dealing with orthosymplectic supergroup over the complex numbers. So this was known before by Layer-Zhang and Helene Layer-Zhang. When you take the odd forms, then you're talking about the periplectic supergroup. And this statement is in a paper by Coulombier and Eric, but the key step in that statement is in this same paper here. Now, over the real numbers, so let me just say the philosophy of the proof is quite simple, but the technical details are quite hard. So that the philosophy is that you complexify and you use the results over the complex numbers, right? So that's not so hard to state. But the details are quite technical, sort of for what Oded asked about. There's not at all uniform. So if you pick real numbers with the identity involution, that's the easiest case. You complexify this category, you just get the complex version of that category. It's not so hard. When you take complex numbers with complex conjugation, or the complex Clifford superalgebra with its anti-involution, when you complexify this unoriented Brouwer category, you actually have to embed it in the superadditive envelope of the oriented Brouwer category. So this is a non-trivial embedding. And it's a little bit technical to show that this embedding has the right properties. And if you take quaternions and you complexify, you're still in the unoriented case, but you still need the superadditive envelope. The strand gets sent to sort of two copies of a strand. And sometimes you need a parity shift if you're doing the sigma equal 1 case. So again, it gets a bit technical, but the idea is you complexify and use the known results of the complex numbers. So you formally add in direct sums of objects. That would be additive envelope. Super, you formally add in potentially parity shifts. Well, that's idempotent completion. I mean, you add in direct sums of objects. Yeah, because our category wasn't pre-additive or anything. You formally add in direct sums. Super, you add in parity shifts as well. So one nice corollary that you get from these results is the following. If you take P, P prime, Q, and Q prime, where P plus Q is the same as P prime plus Q prime, P prime plus Q prime, then OPQ, the category of tensor modules over that. So tensor modules means modules that are summands of the natural one, of tensor powers of the natural one. These two categories of tensor modules are equivalent. And the way you prove that is it's the same modification of the Brouwer category that maps to them. Both maps are full. And because these categories are semi-simple, the kernels are the same. They're the negligible morphisms, and therefore these categories are equivalent. Same thing for unitary and symplectic. This is not really a trivial statement. For instance, if you replace orthogonal by special orthogonal or unitary by special unitary, it's false. So you really need orthogonal and unitary there. And we couldn't find these statements anywhere in the literature, although somehow suspect that they're known to some people. So some final remarks. Even in the non-super cases, even though, so I did everything over in the super world because it unifies things. But even in the non-super world, you get some new things because you get representation theory of real forms of the classical Lie groups. For instance, the unitary group, the indefinite orthogonal groups, for instance, you get new tools for setting them. You also get Schur-Weil type duality statements for these real super algorithms. Let me also mention, by the way, it's really important here that we're talking about real representations of these real supergroups. Complex representations of real supergroups sort of trivially behave just like representations of the complex supergroups, right, by the universal property of complexification. But when you take real representations of real supergroups, then it's more complicated. There also exist quantum versions of all these diagrammatic categories, and then this should be related to representations of real quantum groups. So that's work for the future. Okay, I'll stop there. Thank you.